Good day, everyone, and welcome to another COMSOL Multiphysics lecture series on 3D coil modeling with the AC/DC module. My name is Walter Fry. I'm an applications engineer with COMSOL, and I want to thank everyone for joining us in these times. So before we get into today's talk, a few opening remarks. This lecture series is the fourth in a series that we've been running. All of the previous sessions, including this session, are being recorded and being posted. You will all get an email with the links to the content once it is posted on our website. In the previous series that we've had, we've talked about 2D axisymmetric coil modeling, inductive heating, and modeling of forces, motion, and nonlinearities. And all of those topics, those were addressed in the context of a 2D axisymmetric coil model. This series, we're going to be focusing on 3D coil modeling. And what I want to do right now is just review briefly the two models really that we talked about yesterday of a single conductor coil and a homogenized multi-turn coil. So on the screen here on the left, we see the first model that we looked at, and on the right, we considered the same model with many turns and saw that we could, rather than modeling the turns explicitly, we could model it via an equivalent domain condition. So let's just briefly review those two models and move forward from there. First, we have our model from the first example here of a single coil, a single copper coil, and we saw that we could address that with either the magnetic fields or the magnetic and electric fields interface. And we could see that in terms of the magnetic fields, that those look identical and the currents look identical. And we were able to evaluate the inductance and the resistance. And again, we saw that those were identical using either the magnetic fields or magnetic and electric fields interface. Then we also looked at the approach of using the equivalent geometry that, or a roughly approximately equivalent geometry that does not explicitly model each turn of the wire, but instead draws a geometry that describes the envelope of all the wires. So the geometry that we see up on the screen there is meant to represent a bundle of 10 wires rather than just one wire. And again, we compute here the magnetic field. And the assumption here is that the current is uniformly distributed within this domain. So we don't model the individual turns. That allows us to not have a very fine mesh of the coil domain compared to the first approach that we were using, where we did have to mesh the cross section and describe each turn. And yesterday we also talked a little bit about swept meshing and how that could improve our modeling or our memory requirements. So what we'll do next is talk about other types of coil models that we can consider. So what we'll do here is we're going to start a new model, and we'll again work in 3D and start with the magnetic fields interface, and again start in the stationary regime. And we'll bring in a geometry that's already created. So what we're going to look at next is a coil that is composed of a ribbon of material, a very thin ribbon of material. And just to quickly review how this was created, it's a series of circle operations in the 2D plane that describes a flat spiral coil. There's a couple of cylinders that represent that have a few faces deleted, that jog the coil down, and then an additional straight strip to represent the return. So what we're looking at here is a thin layer of metal in space where the thickness of that metal is so thin that we don't want to explicitly model that. It would be, we'd need to mesh very, very finely, and we don't want to do that. So what we can use instead is a different kind of boundary, a different kind of excitation, a coil boundary excitation. Before we do that, we'll need to add one more part to the geometry here. We'll add a surrounding block of 20 centimeters on the side, and since this coil is centered at the origin, that will sit more or less exactly in the middle there. So what we'll do here, we'll first define a material, and we'll define a material, just a single domain material, because there is just a single domain now in our model. Our models consist of just this one domain with a set of boundaries. Now, the outside boundaries here are the magnetic insulation boundary condition, and that condition does imply that all of these boundaries are perfectly conducting. So we want to give a different boundary condition to the structure itself that we've drawn. And what we'll use here is a coil boundary condition rather than the coil domain condition. So we can see that there's a coil domain condition and also a coil boundary condition. And we'll use now the coil boundary condition, and we'll apply it to all of these faces here. And again, we have here the conductor model. We can choose single coil conductor or homogenized multi-turn. This would actually represent a bundle of wires, but we'll use the single conductor here. We'll specify the excitation of 1 amp, just as we had before, and we'll specify a thickness. So let's say something, so the width of that coil is 5 millimeters. So we'll set the thickness to be much thinner than that. And then we also need to specify the electric conductivity, and that is governed by the materials branch. So if we come back to the materials branch, we can see this stop sign here that we have a set of boundaries that need a material. So what we'll also do is we'll add in the copper material, and we want to apply it to the same set of boundaries that we have here. So we can use this create selection button, and we can name this selection coil. And now we can apply the copper, rather than to a domain, we can apply it to a boundary and to that set of coil boundaries. And now the coil boundary condition will use the electric conductivity that we have from the materials branch. Just as before, we will want to specify an input. So we'll choose one end as the input and another end as the output. We want to have the current flowing from one end of the coil to the other. And just as we did yesterday, we will want to include a coil geometry analysis step in our study. And we'll want to make sure to drag that up above the stationary study step. And we can go ahead and solve that. And we'll go ahead and solve that right now with the default mesh. And just take a quick look at the results. And again, we can see here from the log that we're first solving for the current distribution in the coil, and then solving for the magnetic fields around the coil. And we see here the magnetic fields, and what we can also extract out of here. Let's also make a surface plot of the current. And what we'll actually want to look at here is the surface current density, because the current exists on a surface. And again, we'll want to add a selection to make sure that we're looking just at the coil itself. So we can change the color map there as well. So we can see the current distribution within that coil, and the magnetic fields around that. That actually does look reasonably smooth there in terms of the current, or in terms of the magnetic fields. The current looks quite smooth as well. But let's also talk a little bit about some of the meshing options that we can apply to this kind of structure. Let's switch to the user-controlled meshing sequence, where we can see that right now our mesh is composed of just a default size feature, a normal feature that governs the meshing of everything. We might want to put on a very particular mesh on the coil, and just as yesterday we did swept meshing in 3D. Today, what we'll do is we'll actually do mapped meshing on our set of coil boundaries. And we're going to want to do the mapped meshing prior to the free tetrahedral mesh. So we drag that mapped feature prior to the free tetrahedral mesh. And let's go ahead and build to that selected point in the sequence. So what we see here is just the default mapped mesh, and we can adjust this mapped mesh with a size setting. So we can specify maybe 15 millimeter element size, and that reduces that size a little bit. Let's reduce it just a little bit further, and you can see that we've now reduced the element size along that coil. But we might also want to specify more than one element across the width of this. So we can also add a distribution feature, and that's going to override the size feature. So we can specify 2 elements through the width. And in this little jog section here, where this jogs up and down, we can add another distribution feature to these edges here, such that we get a little bit better distribution, a little bit better distribution of the current, a little bit higher resolution of what's going on right there. And again, the free tetrahedral mesh is just going to transition from that mapped mesh to the tetrahedral mesh with a set of pyramid elements. So if we now go ahead and recompute that solution, and what we'll get is the similar results, but with a higher resolution mesh around the coil. So we can see the number of degrees of freedom here within the coil have just about doubled, and the overall number of degrees of freedom have gone up as well. And once that's done, we can take a look at the results again in terms of the magnetic field. And the current. And we can also extract out the coil resistance, and we'll evaluate that in ohms. So we can see that's about, or actually milliohms. So we can see that it's about 37 milliohms, and we can also evaluate the power and the current and so on. This kind of coil is appropriate if the dimensions of the coil itself are small. The thickness of the winding is small compared to the other dimension. But what we'll look at next now, let's change things around and look at yet another different variation of a coil. What we have here is we have a coil with a relatively large spacing between the windings. What we'll do next is look at now a different kind of coil. So we'll start over again. So we'll start with another new model. And again, start in 3D. Again, using what we'll do here is we'll start with the magnetic fields interface. And again, work in the stationary regime. And bring in another geometry sequence that is a little bit different. Now, what we're looking at is a volumetric coil again. What makes this coil different from the ones that we looked at before, this is a volumetric coil, but you can see that the turns are actually immediately adjacent to each other. The way that we've modeled this geometry is that you have a conductor, a square conductor, and we actually don't model any gap there at all. There's no distance between these turns. So we have a very tightly packed coil. We can consider it that way. So let's go ahead and take a look at what would happen if we solved this model in the way that we've already done. What we'll do here within the geometry is add in a block again, centered at the origin, such that it completely encapsulates our coil. And again, what we'll do is we'll assign material properties, and we'll add the air property, and also the copper material property to our coil domain. And within the magnetic fields, we'll add the coil feature, apply it to this domain, and we'll specify, just as before, we'll specify an input on one side and the output on the other. And within the study, we will add the coil geometry analysis study step prior to the stationary study step. We'll use the default mesh here for this model, and won't worry about refining the mesh here. So we'll go ahead and solve this model as it is with this coil defined in this way. And just go ahead and compute the solution and see what we get. Okay, so now we are looking at the magnetic field, and this is looking a little bit unusual, but it's not quite clear what's going on here. Let's also add in a second plot of a volume plot of not the norm of the magnetic field, but the current, the norm of the current, and that's a variable mf.normj, and we want to make sure to look at that just within the coil itself. And we can also change the coloring here, the color table. And what will also be helpful here will be to add a arrow plot of the current. And again, we want to plot that just on the surfaces of this coil. And we'll increase the number of arrows a little bit and change the coloring and increase our size a little bit. And what we can see here is from these arrows that the current is flowing in, and it's actually flowing both ways around this coil and flowing back out the other side. So the software is actually not recognizing the intermediate boundaries between these terms. We need to explicitly consider that. And the way that we can do that is first within this coil interface, what we can add is we can add an electric insulation boundary condition. Now we're going to want to apply that to all of the boundaries between the coil terms. And there's a nice simple way to select all of those by defining a selection, an explicit selection of boundaries. And we'll just select one of these boundaries here, and then enable this group by continuous tangent. And now what the software will do is it'll auto chain through all of the, basically trace through all of the unambiguous boundaries that are tangent to the first boundary that I selected. And now I can use that selection and apply the electric insulation to all of these boundaries. And what we'll do is we'll go ahead now and resolve the model and see how that affects the results. The first thing that we can see here already is that the number of degrees of freedom in the messages has gone up. Previously, we had about 1,600 degrees of freedom, and now we have almost 1,900 degrees of freedom. So the software has actually introduced additional degrees of freedom to consider that the current is going to be, can be different across this boundary. So we've enforced the condition that there's no current at all to flow between these turns. So the current is forced to flow purely along these turns here. Now this approach that we're looking at here, this is using the magnetic fields interface. And I also want to show the same procedure using the magnetic and electric fields interface, because there's just a little bit more that we can do with that interface. So let's add in here from the AC/DC branch the magnetic and electric fields interface to the same model. And what we'll also do here is we'll add a second study, where in this second study, we'll just solve for the magnetic and electric fields. So I'll leave study 1 as is, and in study 2, we'll solve for the magnetic and electric fields. As we did before, we are going to apply the Ampere's law feature to the air domain, and that leaves us with the Ampere's law and current conservation feature within the coil, and we'll need to apply a set of boundary conditions, a ground boundary condition on one side, and the terminal boundary condition on the other side, and we'll specify a 1 amp current flowing into this coil. And now we want to again consider this electric insulation at all of these boundaries between the terms that we have here. The way that we do so is to first include a boundary condition called magnetic continuity, because the magnetic fields across this gap, we are going to assume that they are continuous. So we will specify magnetic continuity, and to this magnetic continuity condition, we can add the electric insulation subfeature to our set of boundaries that we have. So let's go ahead now and solve this condition in study 2, where we solve for the magnetic and electric fields. So we've now set up the same problem 2 different ways, using both magnetic fields and magnetic and electric fields. And we can see here that we're solving for more degrees of freedom all at the same time. Okay, so now we have the magnetic fields, and those look exactly the same between the 2 interfaces. And let's also look at the current. So this will be the current from the MEF interface. So we'll change the data set around here and change the volume plot not to be the MF, but the MEF. And we'll plot here the current as well. So we can see now that our current distribution from the magnetic and electric field interface is exactly the same. So that's good. But there's even a little bit more that we can do with the magnetic and electric fields interface that we can't do with the magnetic fields interface. We've assumed here and here, we've assumed perfect electric insulation. But what if you have some kind of imperfect conductor or an imperfect insulator sandwiched between these windings? Then what you can add is this contact impedance boundary condition, which again will apply to those same boundaries. And we can see that now it's really only being applied to those boundaries between the coils themselves. And we can specify here the thickness of that layer. Again, let's make that a small value, let's say 0.1 millimeters. And we can specify the electric conductivity and the permittivity of that material, whatever insulative material we have wound between there. So if we leave the conductivity at this value of 1e minus 2, it'll actually probably still be a pretty good insulator. So for illustrative purposes, what I'll do here is I'll make that that thin layer of material relatively high conductivity, just to really illustrate the point here. And we'll go ahead and recompute now the magnetic and electric field solution. All right, very good. So I hear that we have things, you can see that we have the video signal a little bit better now. Okay, so what we've shown here is, or what we're looking at here, is the current distribution with the inclusion of this contact impedance. So we can see that the contact impedance boundary condition does allow the current to flow between these adjacent surface-to-surface contacting condition coil turns. So that feature available within the magnetic and electric fields interface only. Okay. So we've now looked at just about all of the options in terms of exciting various different kinds of coils. What I want to do now is I want to return back to the model that we started off with yesterday. So we'll go ahead and reopen that model. And talk about this model again, where we considered just well, 1.5 turns of a wire with the wires extending to the boundaries. And what we did here in this model was we evaluated the inductance and the resistance. Now, an additional quantity that we're probably interested in here is an estimation of the coil capacitance, the stored electric energy in this model. Now, this is something that we can estimate by adding an electrostatic analysis to the model. So let's go ahead and do that. And what we're doing here to this component is we're adding another physics to our model. We're going to come to the AC/DC branch, the electric currents, or the electric fields and currents interface. And the very first interface we see here is electrostatics. And we can add in electrostatics into our model. Now, the electrostatics interface, that is being applied to all of the domains. But we can say that the electric energy is probably primarily due to the potential difference between the coils themselves. So we don't need to solve for the electrostatic fields within the conductor itself. We'll just solve for the electrostatic fields within the non-coil domains, within any dielectrics within our model. And now the question is, what boundary condition should we apply here? Well, we want to give the electric potential of along the coil itself. And we've actually already computed that electric potential in the magnetic and electric fields interface. Remember that here we were solving for the current conservation. We were solving for the potential drop along the coil. So let's actually go ahead and make a quick plot of that. Let's set up a 3D plot from the results from study 2. And what we'll plot as a volume plot here, is we'll plot the electric potential. Okay, and we'll let the video catch up here. Okay, and we can again see here now that we have the voltage field along the coil, and that varies from 1 volt down to 0 volts. Now, we can use this electric potential that we have right here, this V field, this expression right here, capital V, we can use that within other physics of the model. And we'll use that within the electrostatics interface. We'll add an electric potential condition to the electrostatics interface and apply that condition to all of these faces of the coil. And we'll set that electric potential to capital V. And that's all there is to it. So now we need to add one more study and change around the study settings a little bit. So we're going to add now a stationary study. And in this stationary study, we'll solve just for the electrostatic problem. We do, however, want to use the solution from study 2. In study 2, we solved for the magnetic and electric fields interface, which computes that voltage field, that electric potential field that we were just looking at. And we will want to use that as the boundary condition in the electrostatics problem, which we're solving in study 3. So within study 3, we come to the values of dependent variables, the values of the variables not solved for, and we'll switch that to user-controlled, choose solution, and choose study 2. And we'll just choose the automatic setting here. We don't need to, there is only a single study, solution from study 2, so we don't need to worry about any of these other settings here. So what we're going to be doing now is solving the electrostatics using the solution that we already have, or the potential within the coil. So we can now go ahead and compute study 3. And we'll let that work through. And now what we see here is a plot of the electric potential field in the space around the coil itself. Now the electric potential, that's probably not as interesting as the electric field. So let's go to the electrostatics and plot out, change that to a slice plot of the norm of the electric field. And what we can see here is that the electric field is high between the turns of the coil. So between the turns, you have a turn-to-turn voltage potential difference. So you have a relatively high electric field between these turns. So given this solution, how can we now extract out some kind of estimation of the coil capacitance? Well, along with the electrostatic solution from study 3, we do get the total electric energy in the system. This quantity that we're looking at right here, this variable ES.int.WE, that's the integral of the electric energy integrated over all of the active domains in our electrostatics physics interface. And this expression that we have right here, we can extract the capacitance from that, because this expression that we have for the total electric energy, that is equal to 1/2 of the capacitance times delta V squared. Or if we rearrange the terms a little bit, if we multiply this by 2 and divide by our potential difference of 1 volt squared, then what we'll get here, rather than a unit of joules, we'll get a unit of farads. And we'll go ahead and change that to units of picofarads and evaluate that solution. And we can see that our estimation of the coil capacitance here is about 2 picofarads. Now, we are neglecting things here. we are neglecting the effect of any electric energy within the coil, and we're actually also neglecting what happens between in the section between the wires, where they terminate on the boundary of our modeling domain. So that's the last thing that I want to talk about today is talk about the boundary conditions that we have here and how to interpret them in terms of the magnetic fields. Well, let's go back to the magnetic fields or the magnetic and electric fields. It does not actually matter which one that we work with here. What we're looking at here, we're looking at the plot of the magnetic field, and in this plot, we're looking at a plot of the current magnitude. What I want to do here within this current plot is we'll remove this. We'll delete this plot of the current magnitude, and instead add a arrow surface plot of the. Or actually, no. Before we do that, let's add a arrow volume plot of the current in the magnetic fields interface. And what we'll do is we'll select to plot just the arrows in the coil itself, and we'll increase the number of arrows just a little bit here so that we get a little bit finer resolution. So what we see here is we see the arrows describing the current going from the terminal back to the ground boundary condition. Now, what we're looking at right now, this is actually not quite the complete picture. The magnetic insulation boundary condition that we have in both the magnetic fields and the magnetic and electric field conditions, these boundary conditions represent a boundary that is a perfect electric conductor. So they mean that current can flow without any impedance of the surface. Current can flow along that surface. So we can also add an arrow surface plot, and if we add an arrow surface plot of the currents, we don't see anything in terms of an arrow surface plot. We're just getting the plot of the current in the coil itself. But there's also this surface current that we can plot. And if we plot that, and we'll plot that in the mesh nodes itself of the finite element mesh, we can see that what we have now is we have the current flowing through the coil, out this end, and at this boundary, between these two terminals, the current starts to flow along the surface, and it flows, and we can change the arrow length from proportional to logarithmic to kind of magnify the effect. The current is flowing from the ground back to the terminal. So the magnetic insulation boundary condition is actually providing a closed current loop to this model. So let's change that back to proportional. And it actually provides, and if we look at this current, actually let's plot these arrow lengths as completely normalized. We can see that there's actually current flowing on all of the magnetic insulation boundaries. Although if we look at it proportionally, you can see that there's actually just relatively little current flowing on some of these surfaces. But all of these magnetic insulation boundary conditions, they do represent conductors. They do represent a current return path. So how could we turn that off? How could we say that some of these boundaries are electrically insulating? How can we say that no current would flow along them? Well, within the magnetic fields, or within the magnetic and electric fields, we can add the perfect magnetic conductor boundary condition along these boundaries right here. So we've selected all these 5 boundaries, and we've left this one boundary as magnetic insulation. And what we'll do here is we'll come back to study 1, where we're solving just for the magnetic field interface. And we'll just go ahead and resolve that model very quickly so that we can see the updated plots of the current flow. Okay, so let's take another look now at our current plot. And now we can see that the current is not flowing at all on any of these other surfaces, and quite distinctly is flowing just between these 2 terminals, or between the terminal and ground along this one magnetic insulation face. Now, you might wonder what would happen if we also added the perfect magnetic conductor boundary condition to this face, where we would say that this face also implies that no current can flow back. And if we did try to solve that model, what we would actually see is we'd see that the model would not be able to solve at all. What we'll get here very shortly is we'll get a convergence plot of the iterative solver trying to solve this problem. And in a second here, that convergence plot will come up. And what we can see here is that this convergence plot is not converging, that this line has just completely flattened out. Now, this indicates that we have an ill-posed problem. If we go back and remove that perfect magnetic conductor boundary condition, we've now let the current loop close itself up, and we're back to a well-posed problem that can be solved. So the fundamental lesson here is that in any magnetic fields analysis, you always need to consider a complete closed loop of current, and you do need to know where that current return path is. So what we have here, what we see is the current is flowing through the coil and also returning across this gap between the 2 ends that we have here. So actually what we have here, if we look at it kind of down from the top, is we have an inductive loop of current here, and we kind of have another inductive loop right here as well. So there is an effect of this magnetic insulation. This does have an effect on the overall inductance of the model. So if we were to change the distance to that boundary, it would affect the model results in terms of the inductance. So what we have here is we have a coil above a ground plane. That's one interpretation that we can have of this model. The other interpretation that we can have of these magnetic insulation and perfect magnetic conductor boundary conditions is as a kind of a symmetry plane. And let's go ahead and now visualize that, by taking our results from our first study, and what we're going to do is we're going to mirror them by creating a new data set. So we'll introduce here a 3D data set of type mirror, and we'll take the study 1 data set, and we'll take a plane, an XZ plane data set, and we'll enter the Y coordinate of -10 centimeters. Recall that we had a box that was 10 centimeters in size. We can go ahead and plot that out, but it just gives us the outline here. So what we'll do is we'll come to our current plot here, the plot that we have of our current, and rather than plotting the data set study 1, we'll look at the mirror data set. And what we see now is we see the complete mirrored data, and what we'll need to do here is increase the number of arrows just a little bit here within the coil. And now what we see here is we see that from that symmetry plane, it actually looks like the current is flowing in opposite directions. So what we have to understand here is that the magnetic insulation boundary condition actually it introduces it does not alter the direction of the current vector as it flows normal to the boundary. We can visualize this within the mirror data set by changing the vector transformation to anti-symmetric. So let's go ahead and just change that option within the mirror data set and come back to our current plot. And now we'll remove or disable the arrow surface plot. Now we have here a plot of a volume plot of the current flowing through our model, through our full model here, through our mirrored model. And actually we'll just reduce that just a little bit more so that we get our plot here just right and increase the size of the arrows. So what we now see is a different interpretation of our model. We can actually think of our model that we started with as actually half of a model of two coils in this arrangement that we see right here. So that's another interpretation that we could have of the model that we had. And it's also interesting to think about what the PMC condition that we had applied. What kind of symmetry does that apply? Well, we can visualize that as well with another mirror data set. And let's go ahead now and we can just duplicate this mirror data set. But rather than having the mirror plane be in the ZX, let's have it be in the YZ. And let's again set that at a distance of 10 centimeters and have that be on the data set mirror 2. So now we have the mirror 1 data set and we have the mirror 2 data set. And now what we see here are two coils next to each other. And the PMC condition that will apply the symmetric transform here. So what we see here is that this leads to yet a different interpretation. Let's actually plot this. Let's set this up in the study 1 to make this a little bit less ambiguous here. So on the left side here, we have the original model that we were working with, and the PMC condition that implies this kind of symmetry where the current would flow parallel to itself as you approach the boundary. Meanwhile, if we look at our symmetry across the PMC condition or the magnetic insulation condition, we can see that the current would flow through that boundary. So we can see here now that we have another interpretation of our boundary conditions, of our magnetic insulation and PMC boundary conditions as symmetry boundary conditions. So these kinds of symmetry boundary conditions, these are going to help us reduce the size of our model if we need to, but they do also introduce another question, which is what size of the model what size of the modeling space can we consider? What we've been using here in our models is we've been using an air domain of size 20 centimeters centered around that coil, but what we also want to look at next is how do we truncate our modeling space and remove any ambiguity about the size of the domain that we're working with. But that talk, that will be what we'll talk about tomorrow. And what we'll do in the time that we have remaining is we'll take any questions that have come in about this material. So if you do have questions, just feel free to go ahead and enter them in to the question window there. and I'll look through what questions have come in and take the ones that we can address in the time that we have here. Yeah. Okay. Let's see. There is a question here of if you could solve for the capacitance in a single study. Yes, I mean you can't solve for it in a single study. No, you do need to solve for first. You need to know the voltage distribution along the coil itself, and then use that as input for the electrostatic problem. And again, this capacitance, I should emphasize, it is only an estimation of the capacitance of the coil. Okay. All right. And then, okay. And there are your questions about infinite elements, and that is exactly what we will be talking about tomorrow, as well as questions. I see here a question about the size of the. How do we choose this coil domain size? And that's exactly what we're going to be addressing. Okay. Okay. There's also a question about the meshing techniques that we've talked about, both in terms of the swept meshing that we use here, as well as the mapped meshing that we use for the flat coil. And you know, these meshing techniques, again, to emphasize, these are only you know, these are shortcuts to get you to a decent solution in a relatively reasonable amount of time. You will always want to perform a mesh refinement study, refining these meshes, trying out different meshes, and seeing how the solution changes with respect to mesh refinement. These kinds of meshing techniques that I'm showing here, they do happen to work well in the geometric cases that we're looking at here. They're not necessarily appropriate in all cases, but they do work well for what we're looking at here. There is also a question about plotting electromagnetic forces, and that is a topic that for which I would recommend going back and watching the previous lecture series on computing forces on parts, which we addressed within the context of 2D axisymmetric modeling. But it does, the techniques that we addressed in this previous lecture do apply equivalently to 3D. Okay. All right. Very good. Yes. And then, yes, one more time, as far as the difference between the magnetic insulation boundary condition and the perfect magnetic conductor boundary condition. The magnetic insulation boundary condition, another way to think of this boundary condition is as a perfect electric conductor boundary condition. That means that the tangential electric field is going to be zero along this boundary. The perfect magnetic conductor boundary condition, you can think of it as the opposite. What it means is that the boundary condition, or that you can also say that the electric field the change in the electric field tangent to that boundary doesn't change in the normal direction. You know, these are, or you can think of it as a boundary condition that does not allow any current to flow at all. Again, these are physical interpretations of these boundary conditions that are also mathematically described in the documentation as well. So we'll take it up from here, from this example tomorrow. and investigate questions about how large to make our model, how to truncate our modeling space, and then start to address frequency domain models. So thank you all very much for your time and attention, and please stay safe out there.